Welcome viewers. In this video we'll see the derivation of self-inductance, mutual inductance, coefficient of coupling followed by the problem. First we'll see the self-inductance. The self-inductance refers having only one coil. Mutual inductance means having two coils. So from Faraday's law, changing current will produce an induced EMF in the circuit. Due to rate of change of current, EMF is produced. That EMF will oppose the change in flux. So this is the phenomena. This phenomena is known as a self-inductance. So when the current is flowing through, due to rate of change of current, the EMF is induced. That EMF will oppose the rate of change of flux. So this is the phenomena is known as a self-inductance. Now we'll see the diagram. So consider the coil with n number of turns. So due to self-inductance we are having only one coil with n number of turns. It is connected through the AC supply. V equal to Vm sin omega t. AC voltage is applied to the coil. When the AC voltage is applied, what will happen? The current will flowing through the coil. Right? A coil with n number of turns available, it is energized by the AC voltage. When the AC voltage is given, the current I is flowing through the coil. This current is rate of change of current. Due to AC voltage, this current is rate of change of current. Due to rate of change of current, flux is produced in the coil. The flux is developed in the coil. This flux also rate of change of flux. Due to rate of change of flux, EMF is induced in the coil. Right? So n number of turns the coil available, voltage is applied, current is flowing. Due to rate of change of flux, due to rate of change of current, flux is produced. This flux also rate of change of flux. So due to that, EMF is induced in the coil. So this EMF is depends upon the flux and also it depends upon the current, because the flux is produced from current. So V is depends upon flux as well as the current. Right? So their details are given here. V equal to Vm sin omega t. I is the current. N is number of turns. Pi is the flux. V is the induced EMF. Now we'll see the derivation. What is the self-inductance of the coil? Right? So we need to remember two things. This V is depends upon flux as well as current. Right? So the description is given. If the AC voltage is applied, current will flowing through the circuit. Due to rate of change of current, flux phi is produced in the coil. Due to rate of change of flux, EMF is induced in the coil. Right? So voltage is applied, current is flowing. Due to the rate of change of current, flux is produced. Due to rate of change of flux, EMF is induced in the coil. Now we'll see what is what is this EMF. So this induced EMF is proportional to rate of change of current. V is directly proportional to di by dt. So while equating, we are introducing one constant L. L is nothing but self-inductance. So V equal to L di by dt. That is equation number 1. Right? So this induced EMF is proportional to current. From that we got the equation V equal to L di by dt. You take this equation number 1. Now we'll see the flux. What about the flux? We'll see that. From Faraday's law, this induced EMF is also proportional to d pi by dt, rate of change of flux. From Faraday's law, it is clearly states that the due to rate of change of flux, EMF is produced. So this V is directly proportional to d pi by dt. So while equating, we introduce the constant N, because the flux is depends upon the number of turns in the coil. So V equal to N d pi by dt. You take this equation number 2. So we have one equation. V is directly proportional to L di by dt. Equation 2 is N d pi by dt. So the left hand side is equal. So we can equate the terms available in right hand side. Right? So from equation 1 and 2. So from equation 1 and 2, we can equate L di by dt equal to N d pi by dt, because left hand side is equal, so the terms available in right hand side is equated. So this dt got cancelled. L di equal to n d pi. So from that we can write L equal to n d pi by dt. Right, L equal to n d pi by dt. If permeability is constant, we will take, if the permeability is constant, what will happen? This equation become L equal to n pi by I. Right, the inductance equal to number of turns flux divided by current. L equal to n pi by I. This is the expression for self-inductance. So the definition what is given, the inductance is defined as the rate of total magnetic flux linkage to the current through the coil. The inductance is defined as the rate of total magnetic flux linkage to the current through the coil. Now we'll see the mutual inductance. So mutual inductance, where two conductors are available, two coils are available, coil 1 and 2, they are coupled together. Mutual inductance happen between two coils. So we are here consider two coils, coil 1 and 2, they are coupled together. Refer this diagram. So this is coil 1, this is coil 2. The number of turns in coil 1 is N1, the number of turns in coil 2 is N2. The coil 1 is energized by the supply, AC supply. The coil 1 is given with the AC voltage V1. When the voltage is applied, what will happen? The current will flowing through the coil 1, I1. The current I1 will flowing through the coil 1. So this current is rate of change of current. So due to rate of change of current, flux pi 1 is produced in the coil 1. So this coil 2 is placed nearer, so part of the flux link with the coil 2, that is pi 1 2. Pi 1 is the flux produced in the first coil, part of the flux link with the second coil, that is pi 1 2. That is pi 1 2 is nothing but flux linkage from first coil to second coil. This flux is also rate of change of flux. So due to that, EMF is induced in the second coil. So this EMF is depends upon this flux pi 1 2. This pi 1 2 is depends upon pi 1. This pi 1 is depends upon I1. So this V2 is depends upon pi 1 2 in the second coil and I1 in the first coil. That is an important thing. Flux in the second coil and current in the first coil. Due to the current only this flux is produced. Right. So we have two coils with n number of turns, N1 and N2. Coil 1 is energized by the AC voltage. So the current I1 will flowing through the coil. Due to this rate of change of current, flux pi 1 is produced in the first coil. The flux is linking with the second coil, that is pi 1 2. Due to rate of change of flux, EMF is produced in the second coil. This EMF is depends upon flux in the second coil and current in the first coil. Right. Now we'll see the description. What we discussed, that is given as a description. The AC voltage is applied to coil 1 and current I1 is flows through the coil 1. Due to rate of change of current, flux pi 1 is produced in the coil 1. The part of the flux pi 1 linked with the coil 2, that is pi 1 2. Due to this rate of change of flux, EMF V2 is produced in the second coil. So this induced EMF is proportional to the current in the coil 1, I1. Now we'll go to the derivation. So the EMF induced in the second coil is proportional to current in the first coil. V2 is directly proportional to dI1 by dt. So while equating, we are introducing constant M. M is nothing but mutual inductance. So V2 equal to M dI1 by dt. So the EMF induced in second coil is proportional to the current in the first coil. So we got the equation 1. From Faraday's law, what is V2? V2 is directly proportional to d pi 1 2 divided by dt. Flux in the second coil. D pi 1 2 divided by dt. While equating, we introduce the constant number of turns in the second coil, because pi 1 2 is depends upon number of turns. So V2 equal to N2 d pi 12 divided by dt. This is equation number 2. Right. So now we have two equations. Equation 1 is V2 equal to m di1 by dt. Equation 2 is V2 equal to N2 d pi 12 by dt. This left hand side is equal, so we can equate the terms available in right hand side. So from equation 1 and 2, m di1 by dt equal to N2 d pi 12 divided by dt. So this is depends upon the current, this is depends upon the flux. So dt got cancelled. M di1 equal to N2 d pi 12. From that m equal to N2 d pi 12 divided by di1. Right? If the permeability is constant, then we can take m equal to N2 pi 12 divided by I1. Right? So we got the expression for mutual inductance N2 pi 12 by I1. So this is the flux linkage in the second coil, current in the first coil. So that is the important definition in the mutual inductance. This mutual inductance depends upon flux linkage in the second coil and current in the first coil. So we got one expression. Suppose if we'll go in a reverse order. Suppose the coil 2 is energized by the AC voltage and EMF is induced in the first coil. Then what will happen? We'll see that. We'll follow the same derivation. Similarly, if flux pi 21 is produced by the second coil, current I2 in the EMF V1 is, right? Coil 2 is energized. Current I2 is flowing through the coil 2. And flux pi 21 is produced in the first coil and EMF V1 is produced in the first coil. Just it is reversed. Coil 1 is energized and EMF induced in the second coil, first case. Second one, coil 2 is given with the AC supply and coil 1 is produced with the induced EMF. So just we can change the terms. Now V1 equal to di2 divided by dt. The EMF induced in the first coil is based on the current in the second coil, di2 divided by dt. Here it is reverse. V1 is now changed into V1. di1 changed into di2. So V1 equal to m di2 divided by dt. You take this equation number 3. Right? I think you are able to understand. Now we are energizing the second coil and EMF is induced in the first coil. Right? So from Faraday's law, this V1 is proportional to d pi 21 divided by dt. Here pi 12. First coil to second coil. Here second coil to first coil. So while equating, we need to introduce a constant N1, number of turns available in the first coil. V1 equal to N1 d pi 21 divided by dt. Equation number 4. Now we have two equations, equation 3 and 4. This left hand side is equal, so we can equate the terms available in the right hand side. So from that, equation 3 and 4, m di2 divided by dt equal to N1 d pi 21 divided by dt. So dt got cancelled. M di2 equal to N1 d pi 21. From that, m equal to n pi 21 divided by di2. If permeability is constant, we can write the term m equal to N1 pi 21 divided by I2. So the important thing is mutual inductance is based on flux linkage in the first coil divided by current in the second coil. That is the important thing, because second coil is energized and current is flowing through the second coil. So you can compare these two. This is flux linkage in the second coil, current in the first coil. Flux linkage in the first coil, current in the second coil. So based on that, we can have a definition is available. Mutual inductance between two coils is defined as the rate of induced magnetic flux linkage in one coil. This is nothing but induced magnetic flux linkage. These two terms is the magnetic flux in coil to current through other coil. Right? So N1 means here I2. Here N2 means here I1. So that is the important thing. In self inductance, both are same, only one coil. In mutual inductance means magnetic flux linkage in one coil, current flowing through in another coil. Right? Now we got two expression for mutual inductance. Now we'll go to the coefficient of coupling. So the coefficient of coupling K is nothing but the fraction of total flux produced by one coil linking a second coil is called a coefficient of coupling. That is K equal to pi 12 divided by pi 1. That's a fraction of what is the total flux link produced in the one coil and how much it is linking with the second coil. Pi 12 divided by pi 1. The ratio is nothing but coefficient of coupling. This is the total flux produced in the first coil. In this, how much flux is linked with the second coil, pi 12. So pi 12 divided by pi 1 is nothing but coefficient of coupling. From that we can write, you cross multiply these two. So pi 12 equal to K into pi 1. Similarly, in other case, when the coil 2 is energized, pi 21 divided by pi 2. So from that, pi 21 equal to K into pi 2. Right? So the coefficient of coupling means how it is linking, how much is fully coupled mean entire flux is linking. If 70% mean only 70% of flux is linking. We can find the ratio, how much of flux is linked, how it is coupled together. That can be calculated from the coefficient of coupling. Right? Now we have to have two expression. Pi 12 can be written as K into pi 1. Pi 21 can be written as K into pi 2. Now we'll refer the mutual inductance. There are two expressions available for mutual inductance while referring coil 1 and coil 2. If coil 1 is energized, this is the term. If coil 2 is energized, this is the term. N2 pi 12 divided by I1. N1 pi 21 divided by I2. Now we will multiply on both the side. Both left hand side and right hand side terms are multiplied. M into M square. Then we need to multiply these two terms. N2 pi 12 by I1. N1 pi 21 by I2. Right? Both left hand side and right hand side are multiplied together. So M square equal to N2. This pi 12 can be replaced as, this pi 12 is nothing but K into pi 1. Similarly, pi 21 is K into pi 2. Right? So this pi 12 is now replaced as K into pi 1. Pi 21 is replaced as K into pi 2. Right? Now we have 2K available. So it becomes K square. Right? And the term, the coil 1 terms are written separately. Coil 2 terms are written separately. Right? For example, this N1 pi 1 by I1. N2 pi 2 by I2. Right? Both coil 1 terms and coil 2 terms are written separately. So M square equal to K square. What is this? This is nothing but inductance. Inductance of a coil 1. N pi by I is the general formula. So that can be written as L1. N2 pi 2 by I2 can be written as L2. Self-inductance of the second coil. So from this K square equal to M square by L1 L2. Bring this term in the denominator. So K square equal to M square divided by L1 L2. What is K? Is take the square root. So M divided by square root of L1 L2. So the coefficient of coupling so M square equal to K square L1 L2. K square equal to M square by L1 L2 by taking the square root on both the side. K equal to M divided by square root of L1 L2. So this is the expression for coefficient of coupling. From that we can find how much this coil 1 and 2 are coupled together. Right? It is always less than 1. Why? This pi 12 is less than pi 1. The pi 1 is linking with pi 12. So this value is always less than total flux. Similarly, this value is always less than total flux pi 2. So based on that, K is always less than 1. Right? Now we'll see the problem based on this self-inductance, mutual inductance and coefficient of coupling. Now we'll see the two coils available A and B with 800 turns and 1200 turns. Coil A have 800 turns, coil B have 1200 turns, having the common magnetic circuit. It means coupled together. The current is 0.5 ampere in coil A produce a flux of 3 milliweber. The current flowing through the coil is 0.5, so that it produces 3 milliweber in the first coil, coil A. In that, 80% of flux linked with the coil B. 80% of flux in the coil A linked with the coil B. Then we need to find what is L1, L2 and M. Self-inductance of coil A, self-inductance of coil B and mutual inductance. Right. Now we will refer what are the given data available. For coil A, number of turns available, the flux available. 3 milliweber means 3 into 10 to the power minus 3 Weber. The current also available, 0.5 ampere. The K equal to 80%. That means K equal to 0.8. That is 80% of flux linked with the second coil. For coil B, the number of turns available, 1200. The flux is pi 12. The 80% of pi 1 is available in the pi 12. So 80%, 0.8 into 10 to the 3 into 10 to the power minus 3, it is 2.4 into 10 to the power minus 3 Weber. For coil 2, number of turns available, flux is available. But current is not available in the coil B. Right? For coil A, all are available. N, pi, I all are available. So we can find the inductance of a coil A. L1 equal to N1 pi 1 by I1. Right? N1 is 800 and pi 1 is 3 into 10 to the power minus 3 divided by I1 is 0.5. So that is equal to, by simplifying, we got 4.8 Henry. Right? All the values are available, so we calculated the inductance L1. But coil 2, the current value is not available. So we will find the mutual inductance. From that we can find coil in the inductance in the second coil. So for mutual inductance, these data are available. N2 pi 12 by I1 is available. N2 available, pi 12 available and I1 also available. So that we will find mutual inductance. Then we will find the L2 value. So N2 is 1200 into pi 12 is 80%. That is 2.4 into 10 to the power minus 3 divided by current is 0.5. So that is equal to 5.76 Henry. The mutual inductance between coil A and B is 5.76. Now we have the value of L1 and M. We need to find L2. We know one more value, the coupling coefficient of coupling K is available. So from the coefficient of coupling we can find the L2 value. So M equal to K into square root of L1 L2. So M value is we calculated, K value is also known, L1 also already calculated. So from that we can calculate L2 value. So square on both the side, M square equal to K square L1 L2. So L2 equal to M square divided by K square into L1. Now we substitute the value, L square equal to M square by K square into L1. M square, that a mutual inductance is 5.76 divided by the coefficient of coupling is 0.8, 80%, 0.8. The L1 is 4.8 Henry. So by simplifying this, what we got? 10.8 Henry. The L2, the self-inductance of the second coil is 10.8 Henry. So now we calculated L1 value, then mutual inductance, then L2 value. All three values are calculated. So in this video we discussed the derivation of self-inductance, mutual inductance, coefficient of coupling, followed by one problem based on this. Thank you.